Have you ever really stopped to think about what's powering so much of our lives? We flip a switch, things just work. But what's actually behind it all, and what's the real cost?
Today, we're doing a deep dive into coal. It's a lot more complicated than just a black rock. Our mission here is to dig up the really critical info about coal, how we use it as fuel, and its pretty complex relationship with greenhouse gases. We're leaning heavily on insights from mining and the environment.
And it's definitely going to be a journey. We'll be looking at how coal even forms, the geology side of things, and the chemistry when it burns, all the environmental debates swirling around it, and of course, how it impacts people. Expect some surprising stuff and a pretty frank look at the debates happening right now in science and regulation. Okay, so let's unpack this a bit. We have to start with something that's, well, undeniable. The climate has changed. That's pretty widely accepted. But then, like our source points out, when you get into anthropogenic global warming, AGW, it gets really polarizing. Fast.
Even within the scientific world, there isn't total agreement on every detail. It's complex.
Exactly. And what's interesting is where the agreement is and where it diverges. Most scientists agree human activity, especially burning fossil fuels, has pushed up CO2 levels in the atmosphere. And they also agree that more CO2 does cause warming. That's the greenhouse effect. But the source notes the direct warming from CO2 itself is actually thought to be quite small.
And here's where it gets really interesting, the big point of debate. This thing called sensitivity. The basic idea is, okay, CO2 causes a little warming, but that warming leads to more water evaporating. And water vapor is a major greenhouse gas itself. So the theory goes, this could maybe multiply the initial warming, maybe up to 3 times. And that amplification, that's where the skepticism, as the source presents it, really kicks in. Because what happens to that extra water vapor? Especially how it forms clouds that's still not fully understood. Do clouds cool things down by reflecting sunlight? Or warm things up by trapping heat? It's a huge question. Plus, there's debate about CO2's whole life cycle, how it interacts with the oceans, which is incredibly complex. And the fact that some mathematical models haven't always perfectly predicted what actually happened. That leads some skeptics to think future warming might be pretty small, maybe even beneficial.
Okay, you've got these ongoing scientific debates, but what's happening in the real world because of all this? Clearly, lots of laws, regulations have popped up globally trying to cut CO2 emissions, especially from things like coal. And that's had real effects, right? Closing mines, making it way harder to get money for new coal plants. It's worth pointing out the source itself stays neutral here. It even says the authors have different views, which just shows how tricky this whole topic is. Okay, even with all these debates, coal is fundamental, but how does this stuff actually form? Let's rewind the clock a bit. The geology is pretty amazing.
It really is. The process is called coalification, basically turning old plants' carbon, hydrogen, oxygen into coal, which is mostly just carbon in the end. It happens in roughly 3 stages. First, you get peat forming in a swamp, just layers of dead plants. Then, bacteria and fungi get to work, partly decaying that peat into this gel-like stuff called gitta. Think of it as primordial ooze. And then, that gel gets buried under hundreds, maybe thousands of meters of sediment. The heat and pressure down there cause thermal alteration bituminization, transforming it into different ranks of coal.
Yeah, both the decay and that heating process are super important. They drive off water, they drive off gases like CO2 or methane, and what's left gets more and more concentrated in carbon. That's what bumps up the heat content, the energy, and gives coal its rank.
The scale is just wild to think about. The source mentions a coal seam that's, say, 1 meter thick today. It might have started as a layer of plants 120 meters thick. That's huge. And the time.
Over 200 million years for some of this stuff to form. It's incredible.
And we classify it by rank, based on energy. Exactly. From lowest energy value, you start with peat, then lignite, both pretty low carbon. Then you get subbituminous, moving up to bituminous, which is a big chunk of what's used. And finally, anthracite at the top. That's over 85% carbon, the highest energy stuff.
Okay, so the coal's formed deep down. Now, getting it out, that seems simple, but mining itself releases another greenhouse gas, doesn't it? Methane.
Nice. That's right, methane, CH4. And it's potent. Over a 100-year time scale, it traps something like 20 times more heat than CO2, though it doesn't stick around in the atmosphere as long, maybe 9 to 15 years. And yeah, it gets released during mining operations, both underground and surface mines, when the coal's handled, even after the mine's closed. And there's a specific thing called coal bed methane, CBM. This methane actually forms during the coalification process, gets stored right inside coal in tiny little pores. And here's a wild fact. Coal can hold way more gas, like 6 or 7 times more, than a typical natural gas field at the same size. So when you mine the coal, you release the pressure, and poof, out comes the methane.
Wow. Okay, so if it's that potent, is it just vented? Or can we actually do something with it?
Thankfully, yeah, we often can. The source talks about coal bed methane capture. Originally, the techniques were developed for safety because methane mixed with air between 5 and 15% is explosive, so they had to get it out of deep mines. But now, increasingly, that captured methane is used as an energy source itself, like natural gas. At its peak in the U.S., around 2008, CBM was actually about 7.5% of their total natural gas production. And captured, it can slash methane emissions from a mine by maybe up to 90%.
Okay, capturing methane for fuel, that sounds like a great idea. Turning a problem into a resource. But as always, it's probably not that simple, is it? There must be other complexities, environmental trade-offs.
You nailed it. CBM extraction, while good in some ways, is pretty controversial in others, especially around water. See, to get the methane out, you have to pump out huge amounts of water from the coal seams first. That water is what holds the gas trapped under pressure. And the problem is that CBM-produced water, it's often nasty stuff, high in sodium, dissolved solids, maybe fluoride, chloride, ammonia, metals. There's this measure called the sodium adsorption ratio, SAR. If the water has a high SAR, it can basically wreck soil structure, make it less permeable, hard for plants to grow, increases erosion. And the source points out that the long-term cumulative effects on farming, on fisheries, they're still largely unknown, which is a bit concerning.
Yeah, largely unknown is rarely a good sign. So beyond the water, what about the impact on the land itself, the physical footprint?
Right, it's not just the water. You need roads, lots of well pads. That fragments habitats. Bad for wildlife. Then there's noise pollution. Compressors, drilling rigs, they can be really loud, run constantly, affects animals, affects people living nearby, and just the visual impact. Cleared land, erosion, the equipment, buildings, power lines, it changes the landscape.
And the rules around all this, are they keeping pace?
That's another tricky area. The source says there aren't that many regulations written specifically for CBM. Often operators fall under existing oil and gas rules, but sometimes mining laws apply too. It can get messy. Different rules might even conflict. Creates challenges.
Okay, shifting gears from gas we pull out, let's talk about coal just catching fire. Spontaneous combustion. This isn't striking a match, right? This happens on its own.
Yeah. Exactly. It's a chemical thing. Reactions inside the coal, usually involving oxygen getting absorbed, start generating heat. If that heat builds up faster than it can escape, the temperature inside the coal pile or seam just climbs and climbs until, boom, it ignites. And these fires can smolder underground in coal seams for years, sometimes without even needing much air from the surface. You see them happen in coal seams, underground or exposed at the surface, in big stockpiles of coal, even in the waste rock dumps from mines. The main driver is that oxidation. Coal soaking up oxygen, getting hotter. If it hits around 80 to 120 degrees Celsius, that's the threshold, it starts a slow burn. Then if it keeps going, gets up to maybe 230, 280 C, that's the ignition point, then it becomes a rapid, self-fueling fire. Very hot.
But it's not always just self-heating, is it? Are there other triggers?
Oh, definitely. The source mentions other causes, too. Things like careless work during mining sparks from welding, maybe blasting sets it off. Natural causes, too, like lightning strikes. And sadly, in some developing countries, illegal slash and burn farming can spread to coal outcrops or peatlands, starting massive fires. Even though it's illegal, it happens.
Goodness. So what's the bigger picture impact of these fires, especially if they can just burn on, sometimes hidden underground?
Huge impact. They pump out a lot of air pollution locally, and they're significant sources of greenhouse gases globally. The source gives this really stark example from Indonesia back in 1997. Massive, uncontrolled fires in forests, peat, and coal seams. They released at least 1 billion tons of carbon. That's more than the entire European Union burned in fossil fuels that year. It added maybe half a part per million of CO2 to the whole atmosphere, just from those fires. Plus, burning peat can actually increase methane release later on from the swamps underneath. It's a whole cascade.
Wow. And what makes some coal more likely to do this than others?
Few things. Higher rank coals, the ones with more carbon, tend to be more prone to it. Particle size matters too. Finer coal dust has more surface area, so it oxidizes faster. You need some air supply, obviously. Cracks in the rock, porous ground can feed an underground fire. And moisture's tricky. Too much water actually slows it down. But some moisture seems to help the oxidation continue once it starts. It's a complex balance.
Okay, so after formation, mining hazards, spontaneous fires, we finally get to what most people think of. Burning coal in power plants, those smokestacks. But like you said earlier, it's not just CO2 coming out, is it? It's a whole chemical soup up there.
Absolutely. Those flue gases are a real mix. You've got sulfur dioxides, SO2, nitrogen oxides, NO2, carbon monoxide, CO, carbon dioxide, CO2, of course, plus tiny particles, particulates, organic compounds, even trace metals like mercury. And yeah, each one has its own environmental headache, from health problems for us to damaging plants, corroding buildings, and the big one, climate change with CO2.
Let's break those down. SO2 first, you mentioned acid deposition.
Yeah, sulfur dioxide is a big one for acid rain, or more accurately, acid deposition. It's a major international issue, especially up here in the northern hemisphere. Coal naturally contains sulfur, usually somewhere between 0.5% and maybe 2.5%, but it can be higher, up to 5%. When you burn it without controls, like 95% of that sulfur turns into SO2 gas and goes up the stack. Coal burning is a huge human source of SO2. So how do you deal with it? You can try to use coal that's naturally low in sulfur, but that often costs more. Or you install technology called flue gas desulfurization FGD, basically scrubbers that pull the SO2 out. These FGD systems create byproducts like gypsum, which can sometimes be sold, or elemental sulfur. It leads to interesting policy things too. Like Indonesia, they tend to export their good low sulfur coal and burn the higher sulfur stuff domestically.
Okay, what about NO2, nitrogen oxides? How does that compare?
NO2 control is often less strictly regulated than SO2 in many places. Some countries don't even have a specific standard for it from coal plants. The main way they control it is by modifying how the coal burns combustion modification. And that actually works pretty well. Plus, NO2 is considered way less toxic than SO2, like several orders of magnitude less, according to the source. And now, the big one, CO2. Yeah, CO2. We know it's crucial for the Earth's temperature balance, and the global increase is driving surface warming. Now, mining itself, as we said, is less than 1% of global greenhouse gas emissions, but burning the coal, that's different. Coal is just such a huge part of the global energy picture, about 2/3 of everything mined worldwide, and the numbers are pretty stark. Burning coal, gas, and oil for electricity and heat. That was the single biggest chunk of global greenhouse gas emissions back in 2010, 25%. Industry burning fuel on-site added another 21%. And think about this. For every gram of carbon in the coal you burn, and coal can be 60–80% carbon, you get nearly 4 grams of CO2 out.
That really puts it in perspective, why coal is such a focus in the climate debate, even if digging it up isn't the main emissions source itself.
Exactly. And the picture is mixed globally. Coal use is dropping in places like Europe, North America, even China now is trying to reduce. But it's rising elsewhere. Southeast Asia, India, Pakistan, Bangladesh. Energy demand there is just growing so fast. So realistically, getting rid of coal entirely from the global mix anytime soon doesn't seem likely. And remember the intensity. Burning coal puts out roughly 25% more CO2 than burning oil for the same energy, about 75% more CO2 than burning natural gas.
So given that CO2 intensity and its continued use, what are the solutions people are looking at?
The main technical fixes being explored are carbon capture storage, CCS, and this idea of zero carbon emission plants. CCS involves capturing the CO2 before it leaves the power plant, separating it, and then pumping it deep underground into rock formations for long-term storage. The oil and gas industry actually pioneered some of this stuff, using CO2 to push more oil out of old wells. But CCS is still really under development. The costs are uncertain, it's complex, and importantly, it doesn't actually eliminate the carbon waste, just moves it somewhere else.
Okay, beyond the gases, what about the actual smoke, the particles?
Particulate matter, yeah. Controlling that is actually a fairly mature technology. Most plants use electrostatic precipitators, ESPs. They work by giving the particles an electric charge and then collecting them on plates. They can be really efficient, like 99.5% removal. The worry, though, is about the really tiny particles, the ones just 1 or 2 microns across. ESPs aren't as good at catching those, and those tiny ones are a health concern because they can carry toxic stuff, travel further, and get deeper into your lungs. Also, ESPs don't work quite as well with low-sulfur coal. Another option is bag filters, like giant vacuum cleaner bags. They're better for small particles, but usually cost more to run.
Are there other nasties coming out of the smokestack?
Yeah, a couple more worth mentioning. Organic compounds, like PAHs, polycyclic aromatic hydrocarbons. Some of those are carcinogenic. Thankfully, modern plants with good controls have cut those emissions way down. But trace metals are still a concern, especially mercury. These metals tend to glom onto the smallest ash particles, the ones that are hardest to catch. Coal burning has put a lot of mercury into the atmosphere over the years, and with global energy use rising, mercury emissions are expected to go up too. Global controls right now only make a small dent.
Okay, so after you burn the coal, capture some gases, filter out particles, what's actually left over at the plant?
You're left with ash. There's bottom ash, the heavier stuff that collects at the bottom of the boiler. And then there's fly ash, the finer stuff that's caught by the ESPs or bag filters. Fly ash is usually the majority, maybe 80% of the total ash. Now, some fly ash actually has value. It's often used in making cement or as filler in construction materials. What's not used gets landfilled, But there are still health concerns about the trace metals left in the ash, even in landfills. The source says there's a real divergence of opinion on how risky that is. And that leads to regulatory headaches too, like in Indonesia, where disposing of ash is subject to really strict hazardous waste rules.
Wow. Okay. So, wrapping this up, where does this leave us? We've gone from ancient swamps millions of years ago,
Right.
all the way through mining, methane, spontaneous fires, and the complex soup coming out of power plants. It's been quite the journey.
It really has. And I think this deep dive shows coal is anything but simple, right? Getting it out of the ground, burning it. It involves complex geology, potent gases, real environmental costs for water and land, plus constant challenges with technology and rules. Understanding that whole life cycle from deep earth to the atmosphere, it's just crucial if we want to have informed talks about where our energy comes from.
Yeah, we've seen how one rock can be a power source, a deadly hazard, a fuel you can capture, and a huge source of pollution and emissions. So many different sides to it. So here's something maybe for you, our listener, to chew on. We know global energy demand keeps rising. We've just unpacked all these complex environmental, economic realities around coal. What responsibility do you think we have as consumers, as citizens, in shaping what comes next for energy? And how on earth do we balance all these competing needs? Something to think about.